Okay, hey guys. So appreciate y'all working with me on this today. Um, I am going to go through the notes with you as quickly as possible because, well, I don't want you to have to listen to my voice all day on a video. And also, I think that these notes are pretty much straightforward to the point where I think you can just read through them and be able to get them. Okay, I don't think you really even need me to go through these today. But I'd like to do that with you just so you can have an explanation for each slide. Because most of it is just a review of trig ratios and inverse trig, and then we just do some calculus with basically just plugging into a formula like we did yesterday. Okay, so nothing too bad. So let's go ahead and get started with the warm-up here. So this is just a review of inverse trig ratios, kind of what inverse trig is doing. Okay, so it says rewrite the following expressions in terms of x without any trigonometric or inverse trigonometric functions. Okay, so I basically want it to be equal to something without any of the trig functions into it. Okay, so let's break down what's going on here. Within the first parentheses here of number 1, we first got to figure out what that value is there. Okay, I always start with the values of the inside and work the way out, just like any other function. It wants to know the tan inverse of x divided by 2. Okay, well, inverse functions are restricted. Okay, and we'll talk about this in the next slide, but they're restricted. And if you remember for tan is restricted in the first and fourth quadrant. Okay, positive in the first, negative in the fourth. So since we're dealing with x divided by 2, two positive values, all right, we're going to be restricted in the first quadrant. Now, what an inverse function does is it takes a value that we get, the ratio of the sides of the right triangle that we get, and returns the angle value that we had plugged in. Okay, so that's what's going on right here. We got a side ratio plugged into the tan inverse. Okay, so we have tan inverse of x divided by 2. And if you recall, with tan is associated with opposite over adjacent. All right, think of your SOHCAHTOA there. So let's draw a triangle out that kind of shows this relationship. All right. We are in the first quadrant, like I said. And that means our right triangle is associated with this angle measurement here. And the angle measurement I'm trying to find with the side ratio of the opposite being x and the adjacent being 2. Okay. So, using those values there, we can find the hypotenuse of the triangle with this side ratio as well, right? We have x squared plus 2 squared equals c squared. Okay. And then just do some quick math. X squared plus 4 equals c squared. Okay. And then just trying to solve for c, we got c equals the square root of x squared plus 4. Okay, so the hypotenuse in this equation is equal to the square root of x squared plus 4. Okay, so now we have the side ratios of this right triangle associated with the opposite or adjacent of x divided by 2. Okay, so now I have the angle measurement. Okay, and now I want to know what the sine of that angle measurement is equivalent to. Okay, so I did my tan inverse to figure out what that degree is, or whatever that angle measurement is, and now I'm taking the sine of that, doing the outer function. Well, the sine of that, well, if you think of sine, it's going to be opposite over hypotenuse. Okay, so our final answer in this case would be the opposite, which is x, over the hypotenuse, which is the square root of x squared plus 4. So, in this equation here, I'll get that back. The sine of the tan inverse of x divided by 2 is just x divided by the square root of x squared plus 4. See how that works? It's the same thing over here for number 2. Okay, I'm looking at the cosine of sine inverse of x squared. And we're working with the inverse of sine of x squared first, and since it's just x squared, we know that's x squared over 1. Okay, so we know that the side ratio here is x squared over 1. The side ratio for sine, again, is opposite over hypotenuse. So let's draw that triangle out to figure out, first of all, how to work backwards and then find the cosine of that triangle. Again, it's positive, so with sine inverse, we're restricted to the first quadrant. And here's our triangle. Okay, the opposites will being x squared and the hypotenuse being 1. Okay, doing the Pythagorean theorem again, we can get that the missing leg is the square root of 1 minus x to the 4th. Okay, so I have the triangle with the corresponding side ratios given by side inverse. Now I want to know what the cosine of that angle measurement is. Alright, well the cosine is just the adjacent over hypotenuse, which in this case the adjacent would be the square root of 1 minus x to the 4th, and the hypotenuse would be 1. Or just, for our final answer, the square root of 1 minus x to the 4th. So that is the value of the cosine of sine inverse of x squared without any trig ratios in it. Okay? And again, that's just a little bit of review from pre-calc. To kind of help us understand kind of what the inverse function is doing. Now remember, as we're going to be talking about our trig inverse functions today, remember that none of the 6 trig functions are one-to-one. Therefore, none technically has an inverse. Remember, every time that we talk about the inverse, sine inverse, cosine inverse, that we're looking at a restricted version of it. Okay? Remember, the domain must be restricted to make them one-to-one. And if we're ever dealing with inverses, remember earlier from this week, that they have to be one-to-one to be taking the derivatives and doing stuff with. Okay? So remember, the domain and ranges of the 6 inverse trig functions are given below. And this should be a review for pre-cal, and we talked about this in the review packet a little bit. But like, remember, okay, so sine inverse right here. Okay, its domain is negative 1-to-1. Its range is restricted between negative pi over 2 and pi over 2. Remember what that graph looks like. I'll draw it out to the side right here. Okay, it was a graph. Remember, its domain was between negative 1 and 1, and its range was between pi over 2 and negative pi over 2. And it looks something like this. Because remember, we're just restricting what the graph would look like if it could go continuously, but we have to look at the restricted version. Okay, so there's our restricted graph. And it's the same thing for cosine and for tan and all that good stuff. Like for cosine, for example, it's between negative 1 and 1 as well, but it's restricted to 0 and pi. If I were to draw that out, I'll try to draw it over here to the left of cosine. Okay, it's between negative 1 and 1, but it goes from 0 to pi. Okay, 0 to pi. Remember that graph looks somewhat like this. Okay. So keep those functions kind of in mind as we're going through these problems, that those are the only values that we can look between. Like the range is restricted to negative pi over 2 and pi over 2 for sine, 0 and pi for cosine, and negative pi over 2 to pi over 2 for cosine, but not including the endpoints. Because remember, for the graph of tan, it has asymptotes at those points. So we have the graph looking something like this. Okay, so the yeah. That's what the graph of tan would look like. Remember that tan inverse is the flip of that. So we now have horizontal asymptotes at pi over 2, negative pi over 2. All right. So just keep those graphs in mind as we go through these problems. All right, these next few slides I'm not going to spend too much time on. I might do one example on the board and then just kind of give you the answers for the others. Yeah, so just remember, okay, these next ones you've done before. Okay, you're just trying to find the corresponding angle measurement or radian that gives you these values 1/2, and negative square root of 3. Okay, just notice the inverse function that you're looking at. Remember what its restricted domain is. Okay, remember that an inverse function are restricted. Meaning they got to be 1-to-1. Okay. Now, if any of the values are positive, so if positive, remember that means we're in quadrant 1. If they're negative, it means we're in the restricted negative version for each of these trig functions. Okay, so looking at this first one here, sine inverse of 1/2. Okay, well it's positive. I know I'm in the first quadrant. The corresponding value that gives me a sine value of 1/2 would be pi over 6. Okay, same thing for cosine. The radian measurement that gives me a cosine value of 1/2, that's pi over 3. Okay. Now, tan is, okay, tan inverse here is negative square root of 3. So that means I'm in quadrant 4. Okay. We kind of draw that out for a second. Like if I'm looking at cosine. Okay, remember I said cosine is between zero, the range for cosine is between 0 and pi. I'm looking at my graph. Looks like this. Okay, I'm between those values for cosine. And for sine inverse, remember I said the range is between pi over 2 and negative pi over 2. So here's pi over 2, here's negative pi over 2. So I'm really looking between the first and fourth quadrant. Tan is the same thing. It's between, this range is between pi over 2 and negative pi over 2, but it doesn't include the endpoints because they are asymptotes. So it looks like that. Okay. So if I'm at negative square root of 3, I'm in the fourth quadrant, but it's considered the negative quadrant. Okay. So it's negative, so quadrant 4. And the tan that would give me positive square root of 3 would be pi over 3, but now it's negative pi over 3. So that's just a little bit of review of freak out there. Got to keep that in mind as we're going through having to find these actual values in the derivative of the inverse. Just some more practice of the kind of stuff you saw in warm-up here. Arc sine, sine inverse of 1/3. That gives me, again, the ratio of the opposite over hypotenuse. So you can draw your triangle again. Okay. Again, this is just more stuff from the warm-up here. So if I have the angle measurement with the ratio of the opposite being 1, the hypotenuse being 3, doing some Pythagorean theorem and doing some algebra, you can get that the missing side is the square root of 8. So then I want to know what the tan of the angle of this triangle is. Well, that's just going to be your opposite over adjacent, so that would be 1 over the square root of 8. And same thing over here. We got 3/2. Now that would be your, again, your opposite over your hypotenuse. Okay, but let's draw this one out. Okay, well we got an angle measurement here. It's positive, so the opposite is 3. The hypotenuse is 2. Well, now look at this. The hypotenuse is 2. One of the legs is 3. It is actually impossible for the leg to be greater than the hypotenuse. That's the point of a right triangle, so this one does not exist. And that should make sense because 3/2 is not within my domain. All right, my domain is pi over 2 to negative pi over 2, and 3/2 exceeds that. All right, I'm already going over my limit here that I'm wanting to keep for this video. But this next slide again is just review, okay? It's kind of help you to understand the relationship between a function and its inverse. Well, remember what a function and its inverse does. They undo each other. So if I'm doing the sine inverse of 0.6, and then I take the sine of that, doesn't it just undo it? So wouldn't I be left with 0.6? Okay. That's kind of what all these examples are doing. I don't want to waste too much time on that. Number 3, though, is an example I kind of want you to take note of. Okay, it's not so much that I do the sine of 2 pi over 3 and then undo it and I'm left with 2 pi over 3, because 2 pi over 3 is not within the domain, all right, of sine inverse. So think about this. If I take the sine of 2 pi over 3, well, what is the sine of 2 pi over 3? Well, the sine of pi over 3 is square root of 3 over 2, and since I'm in the second quadrant, it's still positive, so positive square root of 3 over 2. And I'm looking at the sine inverse of that. Well, remember that inverse sine is restricted to the first and fourth quadrant. That's positive, so I've got to be restricted to the first quadrant. And so the radian measure that gives me square root of 3 over 2 in the first quadrant is pi over 3. Okay, but which does correspond with 2 pi over 3. It's going to be the same value for sine. So in a way, yes, it still undoes what you've done. Okay. For number 2, since pi over 12 is in the first quadrant, then the sine inverse just undoes the sine, and we're left with pi over 12. Sine of 3 pi over 4 is not in the first quadrant, but the sine of 3 pi over 4 is not, that's in the second quadrant. That's not within the domain of sine inverse, so you kind of actually have to do a little bit of math there. But it's not too bad. The sine of 3 pi over 4 is just positive square root of 2 over 2. And then the sine inverse of that, restricted to the first quadrant, would just be pi over 4. Again, not too bad. Okay, now for number 5, okay, we got the sine inverse of sine. Well, that just again undoes it because pi over 3 is within the first quadrant. It is within the domain of sine inverse, so we got pi over 3. Okay. Okay, let's go ahead and move on to the next slide. Here, this is just a review of some stuff you already know about the tan inverse, okay, and its limit to infinity and negative infinity. Just some more review to kind of keep in mind as we go through some of these problems later on. Remember that we are bounded in our range between pi over 2 and negative pi over 2. Okay, those are our horizontal asymptotes. And as my tan inverse function goes to positive infinity, okay, it bounds to pi over 2, and as we go to negative infinity to the left direction, it's bounded by negative pi over 2. Okay, so everything up to this point now has all been reviewed Trig. Okay, so sorry if I rushed through it, but I was just trying to get mostly to the new stuff today, the calculus, and that is the derivatives of the inverse functions. And it says the remaining derivatives of the inverse functions can be obtained in a similar fashion. So what I planned on doing was going through with you on how to derive the sine inverse derivative, how we got this derivative right here. But instead, I'm going to leave attached a video from Khan Academy. Okay, so there's a great video on Khan Academy that shows how this derivative was formed. And then by the same type of method, the rest of the derivatives are found to be the same value. So this chart is very important. I'll let Khan Academy explain to you how they came up with these formulas. But for now, just memorize each of these formulas. Okay, I know it seems like a lot, but it's really just going to be kind of 3 formulas if you think about it. Okay, so if I take the derivative of sine inverse of u, whatever my quantity is, it's going to be 1 over the square root of 1 minus u squared times the derivative of whatever u is. It's just x, and don't worry about it. But for some other function, you got to use the chain rule. But notice that the sine inverse derivative and the cosine inverse derivative are the exact same thing except for the negative. Okay? Same thing between tangent and cotangent. They're the same exact formula except that cotangent has a negative. And then again, same thing between cosecant and secant. They are the same exact formula. It's just that cosecant has that negative. Okay, so if you can remember all the non-co ones, so the sine, the tan, and the secant, if you can remember those, and then remember that their corresponding cos, all right, are the same formula but negative, then you should be all set. Okay. So my co-functions our sine and cosine, our tan and cotangent, and secant and cosecant. Okay, so those values are one's positive and one's negative kind of deal. And just remember, with cofunctions, they are equivalent when their angle measurements are complementary. Basically meaning that they add up to 90 degrees. Okay, and we'll discuss that later. Okay, the main thing I wanted to get to today, all right, really the only new thing that we got to today, okay, was that chart that said the derivatives and just doing a couple examples. This is really the main thing. I'm sorry it took 20 minutes to get there, but you know I like to talk. Okay, so our first function here is sine inverse of x to the third power. Now, just using that chart, being able to know what the derivative of sine inverse is, it is 1 divided by the square root of 1 minus whatever our u value is. All right, whatever our u value is. So in this case, it's x cubed goes there, squared, and then times by whatever the derivative of u is. Okay, so just applying the chain rule. All right, so our final answer, if you want to simplify that down, we could say is 3x squared on top, because we are multiplying. And then on bottom, the square root of 1 minus x to the 6th. Okay. All right, this next one's the same way. Now look, we have an outer function, number 2 here. We have an outer function of some quantity cubed. Okay, so this is the chain rule. Okay. Now with chain rule, remember we got to do the power function first. So bring the power down. We have for f prime of x 3, whatever the quantity tan negative or tan inverse of x is, squared. So that's the first derivative. Okay, but then we got to multiply by the derivative of the inside. Okay, so the derivative of tan inverse of x. We're looking back at our chart there. The derivative of that, and just something you have to memorize, is 1 over 1 plus x squared. And that's it. I mean, if you want to multiply across, that's totally fine. I mean, 3 tan inverse x squared over 1 plus x squared. Sure. Let's look at number 3. All right, 3, okay, well, look, we have an x multiplied by the cosine inverse of x. So it looks like we have product rule. Okay, so use what you know about the product rule. Let's take the derivative of the first, which the derivative of x is just 1. Keep the second the same. Plus, keep the first one the same, x, and then take derivative of cosine inverse of x. We're looking back at our chart there. The derivative of cosine inverse is just -1, negative, right, because it's cosine is a cofunction, -1 over the square root of 1 minus x squared. Okay. And, I mean, I'm fine with that as your final answer. If you want to get rid of the ones, maybe kind of make it look a little bit prettier, you can say the cosine inverse x, we'll say minus x over the square root of 1 minus x squared. Isn't that beautiful? Isn't math just beautiful? Okay. So, let's try number 4. Let's try our last one. Okay, now look, it looks like we have base e raised to some function power. Okay, we know how to do this from yesterday. Okay, if I want to find the inverse, or the derivative of this, okay, remember it's going to be, we're taking the derivative of an e to some power, e to the u. Well, remember the derivative of e to the u is just e to the u. So e of cosecant -1 x squared, but we got to multiply, right? We got to multiply by the derivative of u, whatever that quantity is. So the derivative of cosecant inverse of x squared. All right, well, we know what the derivative of cosecant of x squared is from our chart. Okay, it's a co-function, so it's negative 1 over. Now, it says in the chart u squared times the square root of u squared minus 1. Okay, well, our u value here is x squared. Okay, so we have x squared for u. All right, the square root of, instead of u squared, we have x squared squared. Okay, so we're plugging in u as x squared, and that's squared, minus 1. And then, since we took the derivative of that, well, it is chain rule again, because remember how I said we got to multiply the derivative of whatever u is. The derivative of x squared is, I'll write it right here, multiplied by 2x. Okay, so just simplifying down a little bit, that would be e cosecant negative 1x squared, all right, times, and just kind of cleaning up this little fraction here, that would be negative 2x divided by x squared, square root of, x squared to the second would be x to the fourth minus 1. I'm sure we could probably simplify that a little bit more, taking the square root and then simplifying out an x. You can do that, but I'm going to leave it like this for now. Okay? So 26 minutes on this video, could have been done in 5, I realize, but sometimes I talk a little too fast. I don't know. If you made it to the end of this video, great. Awesome. Cool. If you literally listened to the full 27 minutes of me talking, that is unbelievable. I'm proud of you. I will give you a treat. Remind me to give whoever watched this video from 0 minutes to 27 minutes, and without skipping, give you +5 on your next text. Remind me to do that. Everybody's going to wait until the very end, so I doubt anybody's going to be listening to this. Okay, I'm done. We'll answer questions tomorrow. Have a good day.